Hello students, good morning. Let us start the class of analog electronic circuits. In the last class I was discussing this small signal operation and I will continue the same discussion now also, because in the other class suddenly the time was out. So whatever I was discussing the other day, I will explain it once again in brief now. You can see this particular curve. In the x-axis it is VBE, in the y-axis it is IC, which means input voltage versus output current is being plotted here. So such type of curve we generally call it as a transfer characteristics. Transfer characteristics in the sense it is input versus output. Here it is input voltage versus output current, and so we can also call it as it is like a transconductance characteristics. In general, resistance is V by R. Now in this case it is VBE versus IC, so we can call it as a trans resistance characteristics also, or we can call it as a transconductance characteristics also, depending upon how we analyze it. So now in this particular curve, as VBE is slowly rising, IC also slowly rising, but you can see that the curve is not a linear curve. If it is a straight line, we can always predict the value of IC at any point of VBE, and we can simply write an equation for the output resistance itself, or for the transconductance, not for the output resistance as such, for the trans resistance or for the transconductance, in whatever way we analyze it. If at all we write it as VBE by IC, then we can say that it is a trans resistance. That means it is a transfer of resistance from the input side to the output side. But the curve is not linear, which means the trans resistance is changing throughout, which simply means that by using a regular expression for a linear equation, let us say for a linear equation or a straight line, we have a mathematical expression, that is y equals mx plus c. Now we cannot represent this particular curve with respect to that y equals mx plus c. That is the reason in the mathematics subjects you will keep on studying the differential equations, you will keep on studying the quadratic equations. The reason is such curves, such continuously varying curves are part of any engineering science, not just electronics. Such curves are present almost in every engineering science or even in science, because nature itself is non-linear. The nature's response is always a continuously varying response. So that way, when nature itself is non-linear, even the materials with which we are working on are going to exhibit a non-linear behavior. So in such a case, such a curve cannot be represented by means of a straight lines expression. We will have to use either a differential equation, sometimes second order, sometimes third order, or we will have to go for a quadratic equation or cubic equation. That is why in the mathematics courses you will keep on dealing with the quadratic equations or equations of the higher order, or differential equations or equations of the higher order differentiation itself. The more the order, the better is the accuracy. In fact, we cannot fully represent this curve using a single expression, and we always have an approximation here. As it is continuously changing, that is the reason many times we use trigonometric functions and we use the exponential function as well. Why do we use e power x? The reason is e is a continuous number. E is not a single whole number. The value of e is 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial, that way it goes on. Just like pi, e is a never-ending number. So using a never-ending number, as it is a continuous number, we can represent the continuous curves or continuous responses. That is the reason in our engineering sciences we keep on using E, we keep on using trigonometric functions, we keep on using differential equations, we keep on using quadratic equations, and we have many forms of representation like exponential form, Cartesian form, geometric form, and it goes on. As I've been telling you, problem can be a single one, whereas solutions are many. So let me come back to this particular curve itself. As this curve is a non-linear curve, it is not possible to predict the behavior of the circuit well in advance unless we conduct the experiment fully for all the values of VBE. But as I have told you, it is not possible for us to keep on testing the circuits where the devices are much larger in number. I was mentioning about a method called EDA, Electronic Design Automation, where we make use of the computer for all the high level computations which a human being cannot actually do. I keep on telling it humorously in the classes that computer is a high speed, high memory, stupid machine, whereas engineers are low speed, low memory, intelligent people. So, we human beings are lower speed, lower memory people, but we are intelligent people. Whereas computers are having high speed and high memory, but the computers do not know anything on their own because it is nothing but a machine. So, what we do is, wherever we require a high speed, high memory application, we use the computer for electronic design automation. That is the advantage of using computers for engineering sciences or technologies. So we have no other option than to make use of the computers for our computational purposes. In that case, we should model the behavior of the transistor such that this mathematical model, we will put it into the computer. Once we put into the computer, we can easily test any circuit just using the computer without physically connecting the circuit. Such type of testing is called as simulation. Simulation in the sense there is no real component available or there is no real circuit also available. We simply connect those symbols using either PSpice or OrCAD or any such EDA software. We simply connect those symbols as circuits and we apply voltages and we only can plot the characteristics of the circuit, because to the software developer would have provided the models of a resistor, models of a capacitor, models of a transistor, or models of a diode, or models of any electronic device. And that modeling is possible mathematically by means of this particular small signal operation. So that is the purpose of this AC analysis. So now let me come back. What is basically meant by small signal operation? Now look at this curve. You can see that the shape of the output is not the same as the shape of the input. The input signal is having exactly 50% of positive cycle and negative cycle. Whereas at the output you will see that the positive cycle is slightly larger than the negative cycle. As you already know, common emitter configuration is going to provide 180-degree phase shift. So when the input signal is rising, output signal should be falling because the transistor is coming towards saturation. Similarly, when the input signal is falling, output signal should be rising because the transistor is going towards the cutoff region. Otherwise, the transistor is exactly at the middle of the active region. Now, when we apply such a signal, because of this curvature in the characteristics, we will see a distortion at the output. Means it is not actually having a 50% duty cycle, where the amplitude of the negative cycle is smaller in this case than the amplitude of the positive cycle. This is called as amplitude distortion. Means whatever is the shape of the waveform, that is not completely replicated at the output. So this is an amplitude distortion. This distortion is unfaithful. In the sense, we want to have a faithful amplification where the shape of the waveform should be the same at the output as well. But we are not seeing it that way. So now, how do we avoid this distortion? For avoiding the distortion, what we can do from our side is, we cannot change the device as such because device is basically is non-linear itself. So from our side what we can do is, we will not operate this switch or transistor in these 2 points. We will operate within this Q range itself. That means we will apply a signal which is much smaller such that we will not have distortion. I hope you got it now. We will apply a signal around Q. The signal must be much smaller. Signal should not be in volts at all. It should be either in microvolts or in millivolts. So when the signal is small enough, even the distortion can be small enough because it is a smooth curve at that time. We can approximate this particular line which is across Q with a small straight line. Let me draw a small straight line adjacent to this Q, this way. Let us say we have a straight line like this, and let us say we operate this particular transistor with the much smaller signal so that the signal will be having its positive and negative cycle only at the edges of this line which I have drawn. Now in that case, when we get an output, the output will have a lesser distortion or it may not have a distortion at all based on the amplitude of the input signal. That is called as small signal operation. I will repeat this. We will apply an input signal which is small enough such that the output's distortion can be ignored. In such a case, we say that the circuit is under small signal operation. Now, conversely, there can be a large signal operation. In case of a large signal operation, there can be a signal which is large enough which will cause distortion. Such amplifiers are also there. Just like small signal amplifiers, large signal amplifiers are also there. But those amplifiers we are going to discuss in the 5th module in this course. They also have some particular usage. For example, in your mobile phone's charger, there is something called as a class D amplifier, which is part of a switched mode power supply. So there are high frequency switching is happening where even if the distortion is there is no problem for us because we are going to convert that AC into DC for charging our mobile phone. Such circuits are also there. They come under class B, class C, class D amplifiers. Those amplifiers we are going to discuss in the 5th module of our course. So right now whatever amplifier we are discussing, this is called as class A amplifier. Class A amplifier means we want a faithful amplification. We want the shape of the input waveform to be retained at the output. Such amplifiers called as small signal amplifiers, and such operation is called as small signal operation. I hope you got this answer now. If you still have any doubts, you can keep asking me in the chat box. I'll keep watching the chat box for the questions. Now let me continue. This definition I had already read the other day, that's why I am not going through it once again. Now, the total collector current during the working of the amplifier can be expressed as capital IC equals capital ICQ plus small ic, where IC is a AC collector current. Now you already know that we have a quiescent point and we have set the amplifier working at the quiescent point, and that is that ICQ. Now when we apply a small signal, that will introduce a small AC current as well. Now that AC current we write it in a smaller case. Always whenever we write a uppercase alphabet, that means a DC counterpart. Whenever we use a lowercase, then that is an AC counterpart. Always in our circuitry we will have DC and AC together. This I had mentioned you earlier also. All our circuits are DC operated circuits, whereas all the inputs are AC inputs, because all signals are basically AC. So in our circuitry, we will have a combination of DC as well as AC counterparts. Now to minimize the distortion, what we can do is, we can apply the same 10:1 rule, which can say that small IC peak to peak is less than 0.1 ICQ. Just a minute. Let me continue. We had applied this 10:1 rule earlier also for the choice of the value of the capacitors. Now, the small signal operation can be defined this way also, which means the input signal's peak to peak amplitude can be less than 10% of the quiescent current, which means the DC current we already know. The AC current can be much smaller, it can be less than 10% of the DC current. In such a case, we can safely say that it is a small signal operation where the input signal is only 10% of the DC current. Then the Q point will not be affected much. So, that is this particular general methodology for minimizing the distortion. In fact, you can really verify this particular point when you start working on the RC coupled amplifier in the AEC lab when the offline lab classes start, where you can purposefully increase the amplitude of the input signal and you will really see a waveform distortion at the output. You will see the clipping of the waveforms at the output. So, whenever required, when you come back to the college, when you work in the labs, you can call me and I will show you how this distortion really occurs during the lab experiment conduction. Okay, so this particular way of minimizing the input signal such that it is only 10% of the quiescent current. This is a benchmark or a thumb rule for small signal operation. Now, based on the small signal operation, the AC current gain also can be defined. We can define it as beta AC is equal to small ic divided by small ib. Means, just like we have the conventional beta, that beta is capital IC by capital IB. That is the DC current gain. For a small signal operation, we can have the AC current gain as well. That is output AC current divided by input AC current. But it does not matter much here. You don't have to worry that we will have 2 beta now. This is only a theoretical explanation for the beta. Otherwise, we are going to use the same beta even for AC analysis because it does not make much of a difference. The conventional beta is the DC current gain and it utilizes the complete graph of Q point, whereas beta AC occupies only the region of small signal. As the response is considered to be linear, the value of beta AC does not differ much from beta DC because we have considered that across the Q point, because it's a small signal operation, we can consider it as linear. It is a near approximation. So, the value of beta AC does not differ much from beta DC. Now, we can define AC emitter resistance as RE dash equals small VBE divided by small IE. Please understand this. As we are working with the transistor near the Q point, there is a small change in base to emitter voltage for which there will be a large change in emitter current. Now, the emitter region will have a dynamic resistance. If at all that curve which I showed you earlier, if it is taken as a straight line, we can say that it is a static resistance where the resistance is common throughout. But it is not the case because the curve is non-linear. When the response is non-linear, resistance keeps changing point to point. Now, around the Q point, we can consider it as a linear region, very small linear region. There we can measure the emitter's resistance and we call it as a dynamic resistance because we are measuring it only at a particular point. Now, that can be called as AC emitter resistance, and we can give the symbol as RE dash equals small VB by small IB. Now why we have this small Re? Because it is a dynamic resistance or AC resistance. Why we have this dash symbol? With this dash symbol we also call it as prime symbol. We are writing it specifically that way because it is internal to the BJT. Otherwise all other resistors which are external to the transistor, we write them in capital letters. Here we are writing in small letters. Now this should not be confused with the resistance which we are connecting at the emitter. We physically connect one more resistor at the emitter. There we use it as capital RE. So here, to avoid the confusion, the author Malvino uses this dash symbol. Whereas Boylston does not use this dash symbol at all. He directly writes RE in small case. And a small case indicates it is AC resistance. Capital RE indicates it is actual physical resistance. So I am here following the Malvino's convention. Later on I will be telling you about the Boylston's convention also. Later on when we work out exercises, we are simply going to write small RE itself because we know that it is AC resistance. So here the prime symbol dash is used to indicate that the resistance is inside the BJT. As VBE and IE are the very minute quantities that occur around the Q point, the AC emitter resistance can be expressed in a different form as RA dash equals VT by IE. Now please understand this. We define this emitter resistance as VBE by IE. But around the Q point, it is not 0.7 volts. This is not a capital VBE. Please understand that. It is a dynamic change at the base to emitter junction when the input signal is applied, and the input signal is always in microvolts and in millivolts. It is not in volts. So we cannot write capital VBE here. We always write small VBE. And the small VBE is a minute change which is applied at the input side. That is why we have a clear-cut definition that RE dash is small VBE by small IE. It cannot be capital VBE by capital IE. It is not so. Because it is internal to the BJT. It is not a physical resistance there. Now, as it is a dynamic resistance which is occurring exactly at the Q point, now we have something called thermal voltage VT. You have already studied this particular thermal voltage VT in physics. That is nothing but KT by Q. K is Boltzmann's constant, T is temperature, normally we take it as 27 degrees centigrade, and Q is the charge of the electron. That is called as thermal voltage. Now, as we are dealing with the small signal operation, as around the Q point the signal is very small, what we can write is, we can directly write it as RE dash equals VT by IE. This IE is the emitter current itself or the DC current itself. In fact, the ratio of small VBB by small IE is same as the ratio of capital VT by capital IE. Because we are fixing the emitter current by means of our DC analysis. And we know that that is the constant current that is flowing through the transistor at the region of the Q point. Now we know that around the Q point there is a minute change happening. That change is nothing but capital VT, that is KT by Q. It is nothing but the transfer of electrons from the emitter region to the collector region through the base region. That is why the Boltzmann's constant along with the temperature is coming into picture along with the charge of an electron. The mobility of an electron is always dependent on the temperature. That is why that particular complete term KT by Q itself is represented as capital VT, and that itself is called as thermal voltage. So now our life becomes simpler. In the sense, we need not worry much about the dynamically changing values. The dynamically changing ratio we have represented as now a static ratio, where we know what is the value of VT, we know what is the value of IE, we can easily find out the dynamic resistance or the AC resistance of the emitter. Once we find out the AC resistance of the emitter, using this particular factor, we can now write a model for the transistor. Now that is the complete purpose of this lengthy discussion. You may be wondering, why are we dealing with all these small things? Our purpose is what? We want to have a mathematical model for the transistor. Once we have a mathematical model for the transistor, the same model can be written as a C language program or as a MATLAB program, or any normal programming language can be utilized for inputting this particular model into the computer. That is our basic purpose here. So this RA dash equals Vt by IE. Here Vt is the thermal voltage, which is the voltage developed in the semiconductor due to increase in temperature. Even though capital IE equals capital IEQ plus small ie, as capital IEQ is much larger than small ie. We already know IEQ will be in milliamperes, whereas IE will be in microamperes, because we are dealing with small signal operation. We have already seen that thumb rule. So IE can be approximated to IEQ. At 27 degrees centigrade, Vt equals 26 millivolts. At 27 degrees centigrade, K into T divided by Q. K is a constant, Q is a constant. T, if it is considered as 27 degrees centigrade, we get the thermal voltage Vt equals 26 millivolts. You would have already come across this particular term when we are studying physics, engineering physics. So therefore, we can simply write RA dash equals 26 millivolts divided by IE. We will be knowing the value of IE. Now we know this 26 millivolts at 27 degrees centigrade. So we can easily represent the dynamic resistance of the emitter simply by writing this formula 26 millivolts divided by capital IE. Now our life became much more simpler. Using this RA dash, now we will write a model for the transistor. I will be discussing about how we write a model for the transistor now. Let us discuss the transistor model. As the BJT is a non-linear device, it is not possible to apply the laws of circuit theory directly into the amplifier circuit, as I have already told you in detail earlier. All the Ohm's law or Kirchhoff's law cannot be directly applied for the transistor itself because it is a non-linear device. Hence, if the BJT is modeled in terms of standard electrical notations, it is easier to analyze the behavior. Let us model the BJT only around the Q point. Assuming that around the Q point we are working with a small signal, and there we consider it as a linear behavior itself. Now, that is our main point, right? We are operating the transistor only at the Q point. We are not worried about its cutoff region or saturation region. We are working only at the middle of the active region. So it does not matter much for us about its other behaviors. We wanted to characterize its behavior around the Q point itself. So if the BJT is modeled in terms of the standard electrical notations, it is easier to analyze the behavior. Now look at this model. You are able to see this model now. Look at this model. BJT is made up of emitter, base, collector, and I have written the accurate diagram now. You can see I have written the accurate diagram now. In general, in the textbooks, you will see all NPN generally written with the equal area. Unless the authors take care of writing the diagram as per the construction of the transistor, normally the textbook authors sometimes make these mistakes. Of course, there are accurate textbooks also, but in general, the normal textbook authors do not bother much about accurately depicting the transistor's construction. So I have purposefully written a diagram where you can see collector is much larger, base is much smaller, emitter is in in the middle of these two regions. Emitter is somewhat of medium region, largest is collector, smallest is base. That is how transistor is constructed. So that from the emitter, when the electrons move out, only some of them recombine at the base, remaining electrons simply move towards collector. For example, let us say there are 1000 electrons at the emitter, and let us say there are only 10 holes at the base. Out of the 1000 electrons which are coming out of the emitter, only 10 electrons recombine at the base, because the base is a p-type. What happens to remaining 990 electrons? The 990 electrons move towards the collector. Imagine there are around 10,000 electrons at the collector. All these 990 electrons which move towards the collector, they knock all these 10,000 electrons which are at the collector, and totally 10,990 electrons move out of the collector. When electrons move in the other direction, we measure current in the opposite direction, because we measure conventionally current flowing from positive to negative of the power supply. But in effect, it is the electrons moving from the negative to positive of the power supply through the transistor. So that is when we say the transistor is switched on. When the electrons move from emitter to collector, then we say that the transistor is switched on. Now we keep this base only at the middle of the active region, such that the transistor is not completely switched on. At the same time, it is not completely switched off. That is when we say it is half on and half off. Now this is the structure of the BJT, where you can see the AC counterpart. IB, IC and IE are written in small letters, which indicates that we are now discussing the small signal operation of the transistor. Now let us try to represent this transistor in terms of two models. You can see one model called T, and you can see one model called pi. One is T model and one more is pi model. These are called that way because of their shape there. Earlier, T model was popular in the very olden days when the transistor was modeled mathematically. Now pi model is popular because it is very easy to use this pi model. In our exercises, we are going to use this pi model itself. T model I am discussing only for the sake of clarity. Otherwise, in our exercises, we are going to work with pi model itself. Now let me discuss how these models are arrived at. Look at the picture at the left side where you see the BJT's diagram. IB we represent this way. Now from base to emitter there is a PN junction. That is, what is that? VBE. Now we have modeled this small VBE. It is not the capital VBE. Capital VBE is the DC counterpart, whereas we are discussing around the Q point the AC counterpart, that is small VBE. Now the small VBE is there between base and emitter, that is written here. Now this particular base to emitter junction has got its dynamic resistance. The dynamic resistance we are represented as RE dash. We have already obtained its value as 26 millivolts divided by capital IE itself. I expect you to go through this lecture once again until you clearly understand all these concepts. Anyhow, I am going to post the video recording into the YouTube. I expect all of you who are now listening to this class, you again go through today's lecture once again until you understand these concepts clearly and thoroughly. Otherwise, later on when we start working out the exercises, if you don't understand these basics, then you will not be able to understand how the exercises are solved. As far as DC analysis is concerned, it is easy, where we apply a Kirchhoff's voltage law and we have a loop equation, we easily solve. But as far as AC analysis is concerned, you should really understand how we write this model based on the BJT's construction. So I expect that you again go through today's lecture once again, so that basics are thorough with you. Okay. So this PN junction or base to emitter junction we represent in terms of a diode there, because it is nothing but a diode there. Even though base region is smaller, emitter region is bigger, Effectively, it is a diode itself. So, that diode will have its own dynamic resistance. That resistance itself is Re dash now. But what is there at the upper side now? At the upper side, we have that collector current. And we know that in the active region, the collector current is almost constant. Recall the output characteristics of the transistor, where the curve goes up and the curve becomes almost linear type. There we say that the collector current is almost constant. For those of you who do not recall that particular curve, I will write the curve here now. The curve goes like this. Here the x-axis is VCE and y-axis is IC. And this is the curve, where this particular area, we call it as active region area. Whereas this area, we call it as cutoff region. And this area, we call it as saturation region. Wherever the transistor is switching on completely, that is called as saturation region, where VCE is much lesser at that time. Whereas the transistor will have a very less current, IC is very less, then we say call it as cutoff region. But we are using this transistor at half of VCC and half of IC sat. So, we are dealing with the active region. So, in the active region, the collector current is almost constant. So, we can easily represent that constant collector current by means of a current source, and we can write it as small IC. Why we are writing small IC? Again, because we are dealing with small signal operation. So, this is called as a T model. This model was also called as Ebersmole model, because this was the first model that the two scientists developed. It had become quite popular at that time, many decades before. But now this pi model has become popular because it is very easy to use this model, because we can see the input and output distinctly separate in the pi model. Whereas in the T model, input and output are not distinctly separated. Here we can simply say that in the pi model, we can say that there is base to emitter and collector to emitter. We need not worry about base to collector at this point of time. And now look at the pi model and look at the T model. Pi model is derived from T model itself. But how it is written? Just look at this. The collector current is basically constant around the Q point, that is written as one current source from the collector to emitter. Now this Re dash is separated and is written as beta Re dash from base to emitter side. Why? Because the ratio beta is existing between IE and IB. You can ignore that 1 in that 1 plus beta always. So, we can simply write that base and emitter are related by means of the factor beta. So, if at all this dynamic resistance of the emitter, if we have to represent at the input side, what we can do is we can simply multiply it by beta. Because we know that the input current is very less, output current is very high. IB is very less, IE is very high, and they are related by means of the factor beta. So, if we have to represent the dynamic resistance of the emitter at the input side, we can simply multiply that by beta and we can write it as beta Re dash. So, this is called as pi model because it looks like a pi. Of course, it looks like an inverted pi. Whereas this is called as a T model because this looks like a T. Of course, this T is a left side turned T. Anyway, this is a T model and this is a pi model. Now, pi model is easy to visualize, pi model is easy to use. Essentially, both are same. Please understand that T model and pi model are essentially both are same. The only difference is that the dynamic resistance of the emitter is represented directly at the input side. Otherwise, both are same. Now, the advantage with pi model is that you can distinctly visualize input separately, output separately, or you can analyze input circuit separately, output circuit separately, because we have written the diagram in that manner. Otherwise, even T model also can be used for solving the exercises or finding out the mathematical model of the circuitry. Now, this pi model itself is called as RE model by the author Boylestad. Here, Malvino specifically brings history into picture, and Malvino says T model and pi model, which were historically named many decades before. Now, almost T model is obsolete in the sense, it is not obsolete in the sense no one is using T model. Everyone is using pi model because it is easy to use. So, pi model itself is being called by the author Boylestad as RE model. So, during our exercises, we are going to call this pi model itself as RE model, small RE model. Okay. Question now, in pi model, why is beta being multiplied by RE dash? Yes, because the resistance which is at the emitter, we are representing at the base. That's what I told you. Base current is beta times lesser than the emitter current, right? So, if at all we have to represent the resistance at the base, then we can multiply that RE dash by beta. That's all. That is the reason. Okay. Now, the T model, also called as the Eber-Small model, represents the emitter diode as AC resistance and collector diode as current source. As I have told you already, at the region of Q point, because it is in the active region, collector current is almost constant, so we can represent it as a current source. The pi model is obtained from the T model as follows. Z in base or input impedance at the base is nothing but small VBE by small IB. This small VBE is nothing but small IE into RE dash divided by IB. Now this IE by IB is nothing but beta AC into RE dash. And we have already discussed that beta AC and beta DC essentially can be considered as same because we are discussing the small signal operation. So, in that way, as beta AC is approximately equal to beta DC, Z in base or input impedance at the base can be written as beta into RE dash. Even though both models are equivalent, pi model is easier to use than T model as the input and output sides are represented separately. However, in both models, the value of small IC is taken as capital IC. Why? Because as the current is constant in the active region, we will not be using a dynamically changing AC current. We expect or we assume that around the Q point, the transistor is linear for a small signal operation, and we are not worried much about IC equals ICQ plus small IC. That small IC we can ignore and we can always consider capital IC for all our analytical purposes. Now, with this basis, I will end today's class. If there is any question further, you can ask me. There are last 2-3 minutes now. If there are any questions, you can ask me now, or else in the next class, we will find out about how to write the AC equivalent circuit for the DC biasing circuits which we have been using till now. We have been using DC circuits only along with the biasing resistors and along with coupling and bypass and blocking capacitors. So now, how do we write an AC equivalent circuit for the same DC circuit which we have been dealing with till now, and how we can model the transistor using this particular pi model, and how we can arrive at the AC characteristics of the circuit, that we will see in the next class. Okay, I am ending the class now. See you in the next class.